Okay, so check. All right, so today we're going to finish up that last example that we didn't get to last week in B11. And then we'll move on to B12, which is on eigenvalues. So this example, we're talking about matrix norms. So if I have a matrix A, so this is my matrix A, then we're just going to find the one norm and the infinity norm of this matrix. So the one norm is going to be the maximum column sum. So I'm just going to take the maximum sum of each of these columns. So we have absolute value of 1 plus absolute value of 0 plus absolute value of negative 1 or absolute value of 2 plus absolute value of 1 plus absolute value of 0 or absolute value of 3, 0, and 4. So which one of these is going to have the maximum column sum?
The left.
Right, so this, the last column here. So the one norm of A would be 7 in this case. Alright, and then the next one that we're going to look at is the infinity norm. And the infinity norm is the maximum row sum, so we're going to look at the sum of each row here.
It would be the first row, right?
Right. Yes. Alright, so the maximum row sum here, the maximum row sum would be 6. So that's just an example of how to find the one norm or the infinity norm if you're given a certain matrix. So now what we're going to do is move on to section B12, and in this section we talk about eigenvalues and their importance to what we're going to be studying next week, which is iterative methods. Alright, so we've learned what it means for a sequence of vectors to converge to a limit, specifically the limit k approaches infinity of xk minus x equal to 0. However, if we use this definition alone, it might be difficult to determine whether a given vector converges or whether a given sequence of vectors converges. For example, if we are trying to see if something converges to a 0 vector, then it might be difficult to see that by this definition. So, for example, so if we suppose a sequence of vectors is defined this way, so xk plus 1 is given by a, xk, so k equals 0, 1, and so on, for some matrix A, then we want to So for some, so for some matrix A. So these type of sequences arise actually in the study of the convergence of various iterative methods, which is what we're going to talk about next week. Iterative methods for solving systems of linear equations. And so, like I mentioned previously, an important question to ask is whether a sequence of this form converges to the zero vector. So a sequence of this form is going to converge to the zero vector if we have limit of xk, limit as k approaches infinity of xk equals 0 in some vector norm. So by the definition of xk, which we can adjust this definition to be for xk, we have to find the limit as k approaches infinity of ak times an initial guess x0. So this would be a sufficient condition, or we'll actually get to a sufficient condition, but this is what we would have if we have a vector converging to the zero vector. Alright, so from here, if we use the submultiplicative property for matrix norms, then we get this is less than or equal to the norm of A times the norm of x0. So from this, we can see that the sequence will converge to the zero vector if the norm of A is less than 1. But this is only a sufficient condition. It's not necessary. So if we want to get a necessary and sufficient condition, we need to have a better understanding of how of matrix vector multiplication and how it affects the magnitude of a vector. So with this matrix vector multiplication right here. But matrix vector multiplication is a complicated operation. In numerical analysis, we want to try to avoid complicated operations. So the understanding of how a matrix vector multiplication affects the magnitude of a vector may be difficult to acquire unless we somehow simplify matrix vector multiplication. Or if matrix vector can matrix vector multiplication can be simply described. So, can anybody think? So if I just have this multiplication right here, A is a matrix, X is a vector, then what's a way that this can be simply described?
Like a system of linear equations.
Well, what is this equal to? Does any,
The eigenvalues times
right,
that
so
vector.
the eigenvalues, right. That's why eigenvalues are so important, because they simplify this complicated process to scalar vector multiplication.
And then A minus lambda I.
Right, so yeah.
Usually 0.
Right, that's how we get the eigenvalues.
Okay,
But this is why eigenvalues are important, and they actually relate to understanding the convergence of iterative methods for solving linear systems of equations. So, matrix vector multiplication can be simplified to just scalar vector multiplication. We call lambda the eigenvalue. is an eigenvector. So we require that x is not equal to 0. But even if we have x not equal to 0, then we can still have lambda equals 0 for an eigenvalue. And eigenvalues can also be complex. So we can have real 0 or complex eigenvalues. And they can be complex even if we have a matrix A that is real. So like Abdullah was just saying, so if I have 8x minus lambda x equals 0, then I can pull the x out on the right, and we get a minus lambda I times x is equal to 0. So from this, so if lambda is an eigenvalue of a, then a minus lambda I is a singular matrix, and so that means that the determinant of a minus lambda I is equal to 0. So this equation is actually a polynomial in lambda, and it's called the characteristic polynomial, and it's how we find eigenvalues analytically, but not how we would do that numerically. So if A is an n by n matrix, and this is an n degree polynomial, and that means there are how many roots? N roots. Right, if we have an nth degree polynomial, we have n roots. And these roots may repeat. So now, I think I'm going to go to the other board. I'm just going to list a few properties of eigenvalues.
Wait, so how do we know that a minus lambda I is singular? Oh, that's just the condition, right?
Yeah, from this right here, from this matrix times x equal to 0. This is singular matrix. So properties of eigenvalues. Okay, so the first one is if lambda is an eigenvalue of A, then there exists at least one eigenvector of A corresponding to X. So it's just saying if I have an eigenvalue lambda, then there is an eigenvector corresponding to that eigenvalue. So secondly, if there exists an invertible matrix P such that B equals PA P inverse, then the two matrices A and B have the same eigenvalues. And more specifically, we call this right here, PA P inverse, a similarity transformation. we also say that A and B are similar matrices.
Don't they have to be diagonalizable? Or is it something different? Like,
Yeah, I think so, actually.
because that's what I think we did in ODEs a little bit, like.
Yeah.
Okay, but it doesn't play a part here?
No.
Okay.
We just we just really care about whether what the eigenvalues of these two matrices. So if they are similar, then they have the same eigenvalues. So if A is symmetric, meaning that A equals A transpose, then all the eigenvalues are real. So that's an important property too, is if we have a symmetric matrix, then we know their eigenvalues are going to be real. So if A is skew symmetric, meaning that A transpose equals negative A, then the eigenvalues are either real, then the eigenvalues are equal to 0, or they're purely imaginary. So we have a skew symmetric matrix and their eigenvalues are going to be 0, or completely imaginary, so we'll have no complex terms.
They won't have complex terms?
Not in skew symmetric matrix. Just purely imaginary or 0. So if A is a real matrix and we have an eigenvalue that is U plus I omega, then what do we know? We know we have at least one other eigenvalue, and what is that?
-7.
Right. So, all right. So we know that this is also an eigenvalue of A if we have this one. Okay. So let's go to the next one. All right. The next property is if A is a triangular matrix, then diagonal entries are the eigenvalues of A. So
it doesn't matter if it's upper or lower.
No, just the diagonal entries. As long as it's a triangular matrix, then the diagonal entries are going to be the eigenvalues. So reduction to a triangular matrix is really helpful, which is Gaussian elimination, but it's also really expensive. So for different cases, it's best to do different things depending on what you're dealing with. Alright. So the next one, determinant of A is equal to the product of eigenvalues of A, and lastly, the trace of A is equal to the sum of the diagonal entries.
Is this for only triangular matrices or?
For the trace, but so it's also equal to the sum of eigenvalues. So if we're defining the trace, it's going to be equal to the sum of diagonal entries and also the sum of eigenvalues.
So 7 and 8 are for only for triangular ones, right?
Right. So now the determinant, we can find the determinant of a matrix that's not triangular.
By using lambda 1, lambda 2.
Right. But yeah, so this would be for a triangular matrix here. Because if it's equal to the sum of the diagonals, that's when it's triangular, it's only when we have the diagonals to be the eigenvalues too.
Okay, but if it's not triangular, it will still be the sum of the diagonal entries, but it will not be the sum of the eigenvalues.
Right.
Or all of the eigenvalues.
So now when I talked about this before, or when I mentioned just a minute ago, so we have the characteristic polynomial, which is a polynomial in lambda, and then we can find the roots of that, and that's going to give us the eigenvalues. So naturally you would think, well, maybe we could use a root finding method to find the eigenvalues. However, that's in practice, that's typically not the way we find eigenvalues. Eigenvalues are normally computed using iterative methods that use some kind of orthogonal similarity transformation that reduce A to an upper triangular form, and then once we get that, then we've got the eigenvalues. So actually in practice, like in MATLAB, the built-in function roots uses eigenvalue finding methods to find the roots of a polynomial instead of the other way around, where you would have a polynomial and find the roots to get the eigenvalues. And the reason they do that is because these iterative methods for finding eigenvalues are a lot more robust to things like round-off error. So finding eigenvalues and studying eigenvalues is a really important and widespread study that a lot of people do. Alright, so now let's take a look at. So it can be shown that if each eigenvalue of a matrix, let's say this. A satisfies this inequality here, that lambda is less than 1, then for any vector x, we have this. Alright, so this is what we were trying to look at earlier, is if this vector converges to the 0 vector. So now we can see that if we have lambda less than 1,
it does converge to the 0 vector.
Right. So furthermore, the converse of this statement is also true if there exists a vector x such that this right here does not approach 0, so say limit of k approaches infinity of ak times x does not approach 0, then
there's at least one lambda
right.
which is greater than 1.
So at least one of these eigenvalues have to be greater than or equal to 1. So this, after all of this, we can finally reach what we were trying to reach, is a necessary and sufficient condition for which we have convergence to the 0 vector. Alright, so let's see where was that. Alright, so now we're, okay. So we have necessary and sufficient condition for a sequence of vectors of the form xk equal to ak times x0 to converge to the 0 vector. Alright, and so the only thing that we need to check is if the magnitude of the largest eigenvalue is less than 1. So so now for convenience, we'll actually label the largest eigenvalue rho of A. So that's equal to the maximum eigenvalue of A. And rho of A has a name, and we call it the spectral radius.
And that's the largest eigenvalue?
Yes, that's the largest eigenvalue of A. So we can conclude that if we have the sequence of vectors A, 0 converges to 0 vector if and only if rho of A is less than 1. So this is our necessary and sufficient condition for convergence to a 0 vector. For a convergence of a sequence of vectors to a 0 vector. So if we find that the spectral radius is less than 1, then we know that the sequence of vectors is going to converge to the 0 vector. So now we can do an example. I think I'll have one over here. So I have this 3x3 matrix. Alright, and it's triangular, so we can see that the eigenvalues would already be revealed to be 2, 4, and 1. But if we want to take a look at A minus lambda I, where let's just pick out the first eigenvalue, 2. So it's going to be A minus 2I. So it's 2 minus 2, 3, 1.
Right, what did?
So, want to look at this characteristic polynomial in matrix form, then I just said, let's find A minus lambda I, where lambda is an eigenvalue of A. And since we have a triangular matrix, then I just picked
You just picked one.
Yeah, I just picked one. Because we're just going to analyze what this means here. So when I do this, I'm going to get a matrix that has columns that are all 0, at least for the first one. Okay. And so since this matrix right here, A minus 2I, has a column of all zeros, then it means it's singular. But we already know, and that means that 2 is an eigenvalue of A. But we already know that since this is a triangular matrix. Also, we can see that 1, 0, 0 is an eigenvector corresponding to the eigenvalue 2, because this is true right here, because this is E1. So we could multiply this out and see. So this is the first column of identity, but it's also an eigenvector that corresponds to the matrix 2. So since A is upper triangular and its eigenvalues, we see the eigenvalues are 2, 4, and 1. But what would be the spectral radius of this matrix? So let's take a look at the eigenvalues. What
the
are
original?
Yeah, of this matrix right here. So the eigenvalues are 2, 4, and 1. So what would the spectral radius be of this matrix? 4. Yeah. So,
You're saying E1 is an eigenvector associated with lambda 1.
Right.
Like
Yeah.
where lambda 1 is being 2.
2. Right.
Because 2 times E1 gives you that first column.
Exactly.
Okay.
Yes.
Wait, can you say that one more time?
Uh,
You
So-
said E1,
E1 times 2
the eigenvalue.
gives us this first column of A. Because A times E1, let me do this. So if I have my matrix A, and then I multiply by E1, so this is A, and then lambda is 2. So if I do this matrix factor multiplication here, I'm going to get 2 times 1 plus 3 times 0, and then everything else, so 0 times this times this, this times this, this times this, that, and that times that. So everything else is 0. And then of course if I do the scalar vector multiplication, I get 2, 0, 0. So that's what Abdullah was saying. We know that E1, or the vector 1, 0, 0, is an eigenvector corresponding to the eigenvalue 2, because when we multiply 2 times E1, we get the same thing as A times E1. And then just from this example here, you can see the importance of eigenvalues because doing this is a lot easier than doing that, especially if you have a really large example or a really large problem that you're working on. Yes. Yeah, don't be sorry.
So, when we took A and we said A minus 2I, like what was the point of that? What were we trying to get?
Well, there's a couple of different ways that we could look. That was so that we get a column of 0 vectors, which means that we have a singular matrix.
Okay.
But since this is triangular, we really could just look as a diagonal also. So it wasn't necessary to see. But we just wanted to see that we got a column of 0. So that means we have a singular matrix. But just from looking at the example, since it's triangular, we know that those are the eigenvalues already. All right. Okay, so as we continue to talk about the spectral radius, the spectral radius is actually closely related to the induced matrix norm. So remember from Monday, the induced norm, so the 1 norm, the infinity norm, and the 2 norm. The Frobenius norm is not an induced norm. Okay, so if we let lambda be the largest eigenvalue of A, and X be the corresponding eigenvector, then if we have any natural or induced matrix norm, then we have the following. So we're going to say that rho of A times the norm of X equal to the absolute value of lambda times the norm of X. And then by properties of norms, we can move the scalar inside the norm. And then just by the definition of the eigenvalue, we know that A times X is equal to lambda times X. So we have A X. And then using the submultiplicative property, we know that this is less than or equal to the norm of A times the norm of X. So that's, so now if we look at where we started and where we ended up, we can see that rho of A times the norm of X is less than or equal to A times the norm of X. But since we have the norm of X on both sides, we can just say that rho of A is less than or equal to the norm of A in any induced matrix norm. So this is the relationship that we can see between the spectral radius and the matrix norm of A. Where A, so, okay, let's see. I'm going to take another one. continue talking about the relationship between norms and spectral radius. So when A is symmetric, we have that the 2 norm of A is equal to the spectral radius. If you'll remember the definition of the 2 norm of A, it's the square root of the largest eigenvalue of A transpose A. But if we have a matrix that's symmetric, meaning that A equals A transpose, we have A squared. And so then that gets rid of the square root also. So, and then what we have left is the largest eigenvalue of A. So we can see that if A is symmetric, then the 2 norm of A is equal to the spectral radius of A. But in general, if A is not symmetric, any matrix A then we have that the 2 norm is equal to, and then we can just say that this is just the definition of the 2 norm in terms of the spectral radius. So it's just going to be the spectral radius of A transpose A, and the spectral radius is the largest eigenvalue. So this is the definition that we discussed on Monday. Which can be seen to reduce rho of A when A transpose equals A. So that's the symmetric case that we were just talking about. Since in general, rho of AK okay, so that's what we were kind of just talking about up here. So does everybody understand about the 2 norm of A equal to spectral radius?
That's why you can write that?
Yeah, so, well, this is why we can do that. All right, so because the condition so we have the condition rho of A less than 1 is necessary and sufficient if and only if limit as k approaches infinity of x equals 0. So this is a necessary and sufficient condition, but what we were talking about before, and based on the definition of convergence of a sequence of vectors from Monday, then it's possible that we'll have convergence if the norm of A is greater than or equal to 1 for some induced norm, for some induced negative norm. Now, requiring that the norm of A be less than 1 was our sufficient condition that we discussed at the beginning of class. But it is possible for this convergence to happen even if the norm of A is greater than or equal to 1. But however, if rho of A is less than 1, then we can conclude for sure that this will happen, that we get convergence to the 0 vector. Even though the limit of, even if this limit may not exist. So the limit is k approaches infinity equals 0. So in view of definition of a matrix norm, let's see, and go to the next word. Alright, so in view of the definition of a matrix norm, that so we know that this will only happen if and only if what? If and only if A equals 0, then we can conclude that if rho of A is less than 1, then AK converges to the 0 matrix. As K approaches infinity. So in summary, I'm going to write some statements that are equivalent. So if we have one, then the other, it needs the other as well. So if I have rho of A less than 1, then of course, this is what we've been discussing, the limit as K approaches infinity of AKX is going to be equal to 0 for any induced norm.
So if rho of A is less than 1, then number 2 happens?
Yes.
Okay.
So if we have this, then this happens. Also, these other statements are equivalent as well. So if I have the limit as K approaches infinity of AKIJ equal to 0, for IJ equals 1 to what's n. Okay?
IJ like the
So if I have, alright, so IJ.
It's like the IJ entry of.
Right, yeah, so that's what this, the IJ's entry of AK is going to, so the limit is going, as K goes into infinity, equals 0. So that happens if the spectral radius is less than 1.
So each entry is going to 0.
Right, yes. And then the last property that we have is that the limit as K approaches infinity of A, K, I swapped them up. I'll do, this is supposed to be the fourth one. The last one is, I have the norm of AK equal to 0. So here I wrote for any induced norm. We don't have a norm in that statement. That should go here. Alright, so this one's saying if the limit as K approaches infinity of AK is going to go to 0, and all of these are true if I have the spectral radius less than 1. So these are just all different ways of saying the same thing. That we have this sequence of vectors that converges to the 0 vector if this necessary and sufficient statement is true. And so we are done really early today, but that's all I have for today. I figured we would get finished early because there wasn't that much left in this section, in B12, but I didn't know how early. So we're just gonna wait until Monday to start talking about iterative methods. So, I'll have more time to say.
Thanks.